We're going to do a magnetic force problem right now. And this magnetic force problem is a good example of a combination of electricity and magnetism problem combined with a mechanics problem. Okay, we have a solid cylinder here. Solid cylinder. And it has current in it going this way. And so this one is, imagine it's going into the board. And it's on an inclined plane, 40-degree angle. And the height of it is 2 meters. In this region, there's also a magnetic field going this way. Okay? And the magnetic field is 15 degrees from the vertical. Okay? So let's assume the magnetic field is uniform. And it is 0.5 Teslas. Let's say the current in the cylinder is 1.2 amps. And it is a solid cylinder. And we can give the mass of the cylinder. Let's say the mass is 3 kilograms. So we'll make it heavy. We want to know what is the acceleration of the cylinder going down the incline. What is the time that it's going to take to get down. And what is the final velocity. So this is a great example of a physics 1 and a physics 3 problem. Mechanics and electricity and magnetism. So let's analyze what's going to happen to this. So we have, if you look at the cross-sectional area of this, we have the current going into the board this way. See, it's going this way like that. Okay, and then we have the mass, mg, going like that. Okay. And then we have the normal force going like that. And then, of course, if an object is rolling, we have static friction going up the incline. Okay? And we have one extra force. So right now, so far, this would be a mechanics problem. Weight, friction force, normal force. But in this case, we have an extra force because there is a magnetic field and a current. What's going to be the direction of the force due to the magnetic field? Okay, so since the magnetic field is this way, 15 degrees from the vertical, right? It's going to be like that. 15 degrees from the vertical. So let's do the cross product. The force due to the magnetic field is IL crossed into B. So put your forefingers in the direction of the current and then curl them up towards the magnetic field, and your thumb gives you the direction of the force. Okay? I crossed into B. So it's going to be perpendicular this way, FB. Okay? So it's going to act like an extra force pushing the cylinder down the incline, and it's going to increase its acceleration. So we would expect this thing to reach the bottom quicker than it would have if it was just a mechanics problem. Okay? So now let's do the forces and the torques and analyze this motion, and then we'll get the answers. So what are the forces in the x direction? Some of the forces in the x direction is MA, right? Just like in mechanics, we rotate our xy axis. Okay? So, of course, this one will be mg cosine theta. This one will be mg sine theta. And then this is going to be theta. Okay? And then the normal force is going to be along the y direction. Okay, how about this one? If I go like that, what is this angle here? Okay, let's try to analyze that angle. We know that this is 90 degrees, right? The magnetic field is 15 degrees from the vertical. And if I draw this, the x-axis, this is going to be what? 40 degrees, right? 40 degrees. That means this whole thing must also be 40, right? So this one 40, and this one is also 40. Alternate interior angles, right? It looks like this. If this is 40, this is also 40, right? But since this is 15, this is 90, this is going to be, this part has to be 75, right? 15 and 75 make 90, and then this little piece is 15. And then if that little thing is 15, this one is what? 40 minus 15, and that's going to give you 25 degrees. On the side, so the final picture looks like you have a cylinder, you have Fs, you have N, you have mg, and then you have FB, and then you have this angle is 25 degrees, right? With respect to the x-axis. So this is my x-axis down the incline and then y-axis. So let's do our forces. Okay, so force in the x direction. You have FB cos 25. Okay, no, and then you have the downward component of the weight, mg sine theta. And then sine theta, the theta is 40 degrees, right? Minus the friction force, Fs, is equal to what? Mass times acceleration. Okay? So, now we are going to do the vertical forces. N, okay, plus Fb sine of 25, mg cos of 40, right? Because this is 40 degrees, right? It's going to turn out that we're really not going to need the vertical force, because the vertical force is mainly so that we can solve for the normal force, but this problem will not depend on our knowledge of the normal force, because in order to find the friction force, Fs, we'll just analyze the torques on the system, and the torques will already take care of everything, okay? So, how do we do the torques? So, sum of the torques is equal to moment of inertia times alpha, okay? What are the torques on the system? The friction force causes a torque this way, right? It causes it to rotate this way, so the torque due to the friction force is R times Fs, right? Remember, the torque is radius crossed into F, so we have here R crossed into Fs, and it's into the board, okay? Are there any other torques? Normal force doesn't apply a torque, it's along the center of mass. mg is located at the center of mass, and Fb actually causes no torque either, because the magnetic force is directed at the center of mass of the cylinder, so it causes no overall torque, okay? So the only torque in the system is Rfs. Then we're going to set that equal to the moment of inertia. That's where the shape comes in. You ask yourself, is it a solid cylinder, solid sphere, hollow cylinder, hollow sphere? In this case, it's a solid cylinder. So we put m r squared over 2 alpha. R cancels r. Fs is equal to m over 2 r alpha. And then remember, r alpha is a tangential. The tangential acceleration at the edge of the cylinder, and if it is experiencing pure rolling motion, then a tangential will just simply equal a center of mass, right? So it's equal to m a center of mass, and then after that point we don't even put the center of mass. We know that when we say a, we just mean a center of mass. So we say Fs is equal to ma over 2. We take that force and we put it into here. So we don't even utilize this equation, right? In a rolling motion problem, you can't use the equation Fs is equal to mu Sn unless you know that the object is already at the verge of slipping, okay? So since we don't use that equation, we don't even need to know the normal force, okay? So take that, substitute it into here. So now you have Fb cos theta plus mg sine 40, and then we have minus ma over 2 is equal to ma, and then we can take the ma over 2, take it over there, we'll have 3 halves ma, okay? Now what's left to do, our final process is to write down what Fb is, okay? Okay, what is Fb? Let's look at the current. The current is going into the board. The B field is this way, right? So FB is equal to IL crossed into B, right? What are you going to do? You're going to do FB ILB sine of alpha, okay? By alpha, it's the angle between the current and the magnetic field, okay? So it's not necessarily at all related to the angle of inclination of the incline, the 40 degrees, and it's not necessarily related to the 25, or it's not even related to the 15, okay? This angle is the angle between the current and the magnetic field. So if the current is going into the board and the magnetic field is in the plane of the board, what is the angle? Just 90, right? So this angle is 90, therefore sine of the angle is 1. So that's often the point where students might make mistakes when they're doing problems like this. They will not define their angle very correctly, and then they'll get confused between them. They might put 15 here, they might put 25, they might put 40, or some other answers, right? But in this case, it's just really into the board, and in the plane of the board, the angle is 90, okay? So it's not related to the 15 at all. So now we just put that one here. ILB cos 25 plus mg sine 40 equals 3/2 MA, okay? So now it is a matter of just putting in the numbers. The current was 1.2 amps. The problem has to also supply to you what the length of the cylinder is. So let's say the length of the cylinder, and let's say it's a long cylinder, so 4 meters, and that's why it's heavy. So we're going to put here current is equal to 8 meters per second squared. Well, once you get the acceleration of the system, then what do you do? Well, the other parts are pretty simple. V final squared is equal to V initial squared plus 2AD. And then it just becomes a mechanics problem, right? 2 times the acceleration times the distance. So what is the distance? If the height was 2 meters and this one was 40 degrees, the distance is equal to what? Sine of 40 is equal to 2 over d, therefore the distance is equal to 2 over sine 40. So we just put that here. The time you can just do V final is equal to V initial plus AT, and then you put the V final here. A, you put 4.68, and then T. Then you divide the answer we got for the final velocity by the answer that we got for the acceleration. So we got 1.15 seconds. 1.15 seconds. Okay? So you can see a good example of a combination of a magnetic field and a mechanics problem. The acceleration that we got is more than the acceleration the cylinder would have had if there was no magnetic field, because the magnetic field force is pushing it forward, right? What would have happened if there was no magnetic field? This would have disappeared, right? Then what would have been the answer? Mass would have canceled. So when there's no magnetic field, the acceleration is independent of the mass. The answer is A is equal to what? 2/3 g sine 40. Therefore, the acceleration only depends on the shape of the cylinder, not its mass. So if we calculate just per second squared, so 4 point something like 19, here we got 4.68, right? So we got a bigger acceleration. So I can change the magnetic field direction. I can make the magnetic field up, I can make the magnetic field down, I could make it so that the magnetic force is up the incline. So I can make this acceleration if I wanted to, I can make it even less than this acceleration by changing my direction of the magnetic field, okay? So hope this helps and it gives you a good illustration of a combination problem. Thank you.